So now we're going to look at some common igneous rocks of different composition. We're going to start with common felsic igneous rocks, and the most common felsic igneous rock is granite. So granite is an intrusive igneous rock. It's phaneritic, has a phaneritic texture, and because it's felsic, it gets composed predominantly of light-colored silicates. It's the main constituent of the continental crust. Now, if this magma, this felsic magma, does not stagnate beneath the surface, if it makes it to the surface where it rapidly cools, it'll form another type of felsic igneous rock, and it'll be rhyolite. So rhyolite and granite have the same chemical composition, but rhyolite is an extrusive igneous rock because it formed from the rapid cooling molten rock at or near the surface. And because of that, it has an aphanitic texture. And because it's felsic, it's composed mostly of the light-colored silicates. Then we have obsidian. It's also an extrusive felsic igneous rock. You say, wait, that's dark in color. That looks like it's made mostly of ferromagnesian silicates, not non-ferromagnesian silicates. It should be mafic. But obsidian is a little bit of an oddball in that sense, because even though it is felsic, even though it's dark in color, it is felsic. It's partly due to its glassy texture that gives it its dark color, but it is felsic. Generally, a light-colored igneous rock is felsic, a dark-colored igneous rock is mafic, and a grayish one is intermediate, but obsidian is the only exception to that rule. Next, we're going to look at intermediate igneous rocks, those with the intermediate composition. The most common is andesite. It's an extrusive igneous rock with an aphanitic texture, medium gray in color. It's mostly found along subduction zone volcanoes. So you can find this in Japan, in the Andes, in the Cascades of Washington and Oregon. But if this intermediate magma does not reach the surface, where it can cool rapidly to form andesite, and if it cools slowly deep beneath the surface, it forms the intrusive intermediate igneous rock, diorite. And diorite has a phaneritic texture, as you can see these large mineral crystals. And so sometimes diorite can look like granite, but it doesn't have it does not have really that many, that large of a diversity of non-ferromagnesian silicates. It doesn't have any quartz. It doesn't have any potassium feldspar. It really only has plagioclase feldspar, which is the white mineral. So if there's any pink in it, if there's any clear minerals in it, that means it's granite, not diorite. So then we have mafic igneous rocks. The most common mafic igneous rock is basalt. So basalt is an extrusive igneous rock with an aphanitic texture. It's very dark green, sometimes it just looks black. And it's the most common extrusive igneous rock of all of them. It's composed primarily of dark silicates, which are rich in iron magnesium, which is why it's mafic. And it's the primary constituent of oceanic crust. And it's also found at lava flows around Hawaii and Iceland. If the mafic magma that forms basalt doesn't make it to the surface and it cools slowly beneath the surface, it'll form the intrusive mafic igneous rock, gabbro. And gabbro has the large coarse mineral texture, a phaneritic texture that most intrusive igneous rocks have. Now this chart just kind of summarizes what we talked about, at least the top 6. It has the 3 compositions, felsic, intermediate, and mafic, and then the phaneritic and aphanitic versions of each composition. So the phaneritic felsic igneous rock, or you can think of phaneritic as intrusive and aphanitic as extrusive. So the intrusive felsic igneous rock is granite, intrusive intermediate igneous rock is diorite, and the intrusive mafic igneous rock is gabbro. And the extrusive or aphanitic felsic igneous rock is rhyolite, the extrusive intermediate igneous rock is andesite, and the extrusive mafic igneous rock is basalt. So Igneous rocks are formed from magma, but where does magma come from? So all magma is generated in the mantle, okay, the partial melting of mantle rock. And thus, mantle rock being extremely dense and having a lot of iron magnesium, whenever mantle rock partially melts, it forms mafic magma. So all magma starts off being mafic in composition. And there's two main processes which are responsible for the generation of magma in the mantle. And we discussed these processes in plate tectonics. We talked about plate tectonics. They are decompression melting and volatile induced melting. So what happens in decompression melting? Well, you can see on this graph, the y-axis over here on the left is pressure in kilobars, increasing downward. And the y-axis on the right is depth in kilometers. And so these pressures on the left y-axis correspond to these depths on the right y-axis. And on the x-axis in the bottom is temperature in degrees centigrade, increasing from left to right. So if you look at this bottom circle, let's say this is rock in a convective upwelling. It's rising from large depths in the mantle to shallow depths. And so as it ascends towards the surface, its depth decreases, and so does its pressure. But its temperature does not really change. So its pressure and temperature conditions, it would be just plotted. The change in them would just be plotted as a vertical line. Now you see this thick blue line. This is the solidus. What this means is that any pressure and temperature over here to the left of it, the rock is completely stable as a solid. So the rock down here at this depth and this temperature is completely stable as a solid. But any temperature or pressure to the right of the solidus, the rock is not completely stable as a solid. And at these pressures and temperatures, the rock will be partially molten. These dashed lines tell you how much of the rock would be molten at different pressures and temperatures. So anywhere along any pressure temperature along this dashed line, for example, the rock would be 80% molten. Then this thick orange line over here, that's liquidus, which means the rock at any pressure or temperature to the right of it, the rock will be completely molten. So as mantle rock ascends in a convective upwelling, its temperature doesn't decrease, but as it decreases in the depth, its pressure does. And you can see as you decrease the pressure of that rock as it goes to lower pressures, it crosses the solidus, and that is why the rock partially melts. The rock is no longer completely stable as a solid at those low temperatures and these high at these low pressures and this high of temperatures. This happens at divergent plate boundaries where you have convective upwellings or hot spots where these mantle plumes bring very hot mantle material from large depths. The second process is volatile induced melting, and this occurs whenever mantle rock is infused with water. And so we have the same graph as we looked at last time, and so you can see the rock right here is to the left of the solidus, so it's completely stable as a solid. Now, as this rock is infused with water, what happens is its pressure isn't changed because it doesn't ascend or descend, and its temperature isn't changed. What changes is whenever you infuse the water with rock, the solidus is actually different. It has what's called a wet melting curve. So now the rock, which was stable at that pressure and temperature, once infused with water, it's no longer stable. So it's to the right of the wet melting curve, so the rock partially melts. And this happens at subduction zones, where the subducting oceanic lithosphere transports water down into the mantle. That water is liberated whenever the crustal rock, the oceanic crust, goes through these chemical reactions known as metamorphic reactions due to the high pressure and temperature conditions. And that water is released into the overlying mantle rock. The infusion of that water into this mantle rock causes it to partially melt, resulting in the magma that fuels the volcanism along subduction zones. So how do we explain the compositional spectrum of igneous rocks, Felsic, intermediate, and mafic, if all magmas originate from melting of mantle rock, which forms mafic magma? How does that mafic magma get turned into intermediate or felsic magma so that it can cool to form intermediate or felsic igneous rocks? Well, Bowen's reaction series explains how magmas change as they cool. Bowen's reaction series illustrates how different minerals begin to crystallize out of the melt at different temperatures as the magma cools. So the process of certain minerals crystallizing and settling out of the melt to the bottom as the magma cools is called crystal settling. So when these crystals solidify out of the melt, being a solid, they are now more dense than the melt, and they settle to the bottom of the magma chamber. But by forming and settling out, they are slowly changing the chemical composition of the melt, because those ions that were in the melt are now removed in order to form the mineral crystal. So here's a figure illustrating Bowen's reaction series. So let's start with mafic magma, which is very, very warm, because mafic magma consists mostly of ferromagnesian silicates. It has a ton of iron and magnesium. And these ferromagnesian silicates have very high melting temperatures. So they don't melt until very high temperatures, and they don't cool until they fall below those very high temperatures. So let's say if we have magma around 1200 degrees centigrade. As we begin to cool it, the first minerals to crystallize out are olivine, and then some pyroxene, and some calcium-rich plagioclase feldspar. So as this mafic magma cools, and olivine and pyroxene mineral crystals are forming and settling out of the melt, they are removing iron and magnesium out of the melt. The iron and magnesium is going into forming those mineral crystals, which are settling out of the melt. And the olivine and pyroxene, they don't have a lot of silica in them, so they're not taking that much of the silica tetrahedra out of the melt. Because if you remember, olivine is the isolated tetrahedra, and pyroxene is the single chain tetrahedra. And so as the olivine and pyroxene form and settle out, they are removing iron and magnesium from the melt, thus making it a little bit less mafic and a little bit more intermediate. And as the magma begins to cool even more, amphibole starts to crystallize out, and more plagioclase feldspar crystallizes out, and then as it cools even more, biotite begins to crystallize out. And as the biotite and amphibole crystallize out, they're removing more iron magnesium. So as they crystallize out, eventually they remove enough iron magnesium, but there's very little left in the melt. And the remaining melt is mostly silica. Silica and sodium and potassium. And so whenever that silica, aluminum, sodium, potassium crystallize, they form felsic minerals. Non-ferromagnesian minerals. And so that is felsic magma. So as mafic magma slowly begins to cool, ferromagnesian silicates, they crystallize and settle out of the melt, removing iron magnesium from the melt, depleting the melt of the iron magnesium and enriching it in silica, thus slowly transforming the melt from mafic in composition to intermediate to felsic. This process is called magma differentiation. So crystal settling causes the composition of magma to change by removing ions that have crystallized out, mainly iron and magnesium. As the dark silicates crystallize and settle out, the magma becomes more felsic in composition. And the formation of magmas with different composition other than the original magma is known as magma differentiation. So this is how felsic and intermediate magmas form, which then cool to and solidify to form felsic and intermediate igneous rocks.
So let's say we had a magma body, and it's mafic composition. As it slowly begins to cool, olivine and pyroxene and plagioclase feldspar, they begin to crystallize and settle out of the melt, removing iron magnesium from the melt, making the remaining melt less mafic and more intermediate. And as more ferromagnesium silicates crystallize out like hornblende and biotite, removing even more iron magnesium, the remaining melt transforms from being less intermediate and more felsic. And so, because all the olivine and pyroxene crystallize and settle out first, the rock that forms the bottom of the magma chamber as it cools is going to be mafic, and it's going to be intrusive because it forms slowly deep at the surface. So that would form gabbro. And then we'd have some amphibole, some biotite, and a lot of plagioclase feldspar crystallizing and settling out next. And that forms the intrusive intermediate igneous rock, diorite. And then whenever the only melt left is felsic, whenever that felsic melt crystallizes and cools, it forms an intrusive igneous rock with mostly non-ferromagnesian silicates, which forms granite. So that's why we find so much of granite in the crust, because whenever this melt solidifies, cools slowly beneath the surface, granite is the intrusive igneous rock that's found at the top of the magma body. So now we're going to talk about intrusive igneous activity. So intrusions, sometimes referred to as plutons, are structures that result from the emplacement of magma into pre-existing rock. So magma can move into and intrude into already existing rock and then slowly cool. Or it doesn't have to be slowly, but then can cool to form igneous rock. So these intrusions, they come in a variety of shapes and sizes. We're going to talk about dikes, sills, and batholiths. So first we're going to talk about these smaller tabular intrusive bodies called dikes and sills. Excuse me. So they're tabular because they're two-dimensional. So see how the dike in the sill, they extend in 2 dimensions, but not in the third. They're very thin in the 3rd dimension. Dikes are discordant tabular intrusions. Discordant means they cut across the existing structures. So here you can see these layers of rock that are horizontal. The dike is cutting vertically up through them, making them discordant. Where sills are concordant tabular igneous intrusions, where the molten rock intrudes in parallel to the existing structure. So the sill, the molten rock intrudes in between the layers of pre-existing rock. And so here you can see this is a sill. This is a layer of basalt that intruded in between this rock below and this rock above, forming a sill, an intrusion of basalt. And this is a dike, where this was igneous rock. This is basalt too, that intruded into horizontal sedimentary rocks. Sedimentary rocks are weaker than igneous rocks, so they erode away more quickly than igneous rocks. And so the sedimentary rocks that this molten rock intruded into have since eroded away, exposing this igneous rock, forming kind of like this natural wall. So this tabular feature of igneous rock once intruded into sedimentary rock that existed here and has now been exposed by erosion. Now, more massive intrusive bodies are batholiths. Batholiths are these extremely large linear structures of igneous intrusions, so several hundreds of kilometers long. They usually form beneath subduction zones, or these large magma chambers that feed volcanoes to slowly cool to form igneous rock. So these magma chambers intrude into this pre-existing rock, but they're large intrusions known as batholiths. So here you can see all this magma that has intruded in here, forming these, feeding these volcanoes, As slowly cools, it forms these batholiths. And so, if you fast forward, this volcanism goes extinct, and all you have are these large volumes of intrusive igneous rock. And over time, as erosion erodes away the overlying rock, those batholiths are exposed. But because the igneous rock is very strong, more erosion resistant, the rock around them is eroded faster than they are, and so erosion actually carves the igneous rock out, forming somewhat of some topography or mountains. So you could see here, these mountains here, these are the Sierra Nevadas in California, and these are batholiths. These are large expanses of granite. These were once bodies of molten rock that slowly cooled beneath the surface. You could see how much molten rock there was in this location beneath the surface. A great deal. And this was molten rock that intruded into pre-existing rock. But that rock that this molten rock intruded into has since eroded away, exposing these igneous batholiths, which is pretty amazing. And so another picture of the Sierra Nevadas here. And you can see these red blotches on the map. This is the west coast of North America. This being British Columbia on the left, on the top, and Washington State, Oregon, California. These large blobs are batholiths, large intrusions of igneous rock that slowly cooled beneath the surface. Because subduction used to occur along the coast in these areas, and these large bodies of molten rock were feeding the volcanoes. And I should note that all this molten rock was produced by that volatile induced melting on the subduction zone. And subduction has since gone extinct there. It still occurs in between right here. It still occurs right here. So that's why these are active volcanoes right there. But it's gone extinct down here and up here. But erosion has exposed those large batholiths, those large bodies of molten rock that slowly cooled beneath the surface. And those batholiths being exposed by erosion formed kind of these mountains, like the Sierra Nevadas, for example. And so they're made of mostly granite because it's at the top of the batholith, which we saw that due to crystal settling, felsic igneous rocks are the last ones to form, crystallize out at the top of the magma chamber. And they're going to be intrusive because they cooled slowly beneath the surface. So a felsic intrusive igneous rock is granite. So that's why most of these batholiths are composed of granite. So that concludes our lecture on igneous rocks. If you have any questions, please let me know via email or ask me in class the next time we meet. Thank you very much.